My name is Dipanshu, and we are here today as part of our final presentation for the CSCI E95 compiler class, where we spend like a semester on making our own functional compiler. Let's get started. The compiler final project, the overview is that we try to make a compiler for a subset of the C programming language. It's a subset in the sense that it does not support all the features of C, especially things like structures and enums. Um, the way we went about this is we made like the front end of the compiler, what I consider that creates like the base for the rest of the compiler. So it checks for correctness of the incoming programs, and then the backend of the compiler converts the processed user programs into MIPS assembly machine instructions so that it can be executed by an operating system. Now, the tools that I rather used for this is very specific to the language that I used. I did most of my implementation in C, um, and it had its own strengths and disadvantages. Some of them being that the code went, the project became too bloated, and some of the fun parts being that you could implement almost all of the parts without relying on many standard libraries. So I used GDB and even Valgrind extensively for debugging some nasty seg faults and um, you know some of these infinite loops that I kept encountering in the course. And I used GraphViz a lot to visualize the tree that I was creating. Um, I also used the YY debug option that comes with Bison to kind of check out the logs and to see how Bison kind of makes internally, it kind of makes the state machines that in turn create your output. I found that very useful in debugging. The compiler design process, like I said, was comprised of the front end and the back end. So the front end would involve the lexer, the parser, symbol table, and type checking. So the lexer basically processes your user program to create tokens, individual tokens that it recognizes and are defined. A parser looks at these tokens and creates an abstract syntax tree using some predefined grammar constructs that we have programmed into the compiler. The symbol table uses the abstract syntax tree, recurses through it, and builds like a lookup table of all the identifiers that have been um, used by the programmer. And the type checking uses both the symbol table and the the abstract syntax tree to kind of do the type conversions, the type promotions that the user did not explicitly perform. The intermediate representation takes the output from the type checking phase, which is basically a fully type correct abstract syntax tree, and uses a symbol table to create a representation of doubly linked lists that the the machine can more or less understand, and the MIPS stage kind of takes the intermediate representation and fully converts it to code that can be executed at the assembly level. So let me begin by showing you some of the outputs of some of the stages. So this is the output of the Lexer. As you can see, it is processing an input program, and it's kind of giving me all the tokens where that it has processed, including the line numbers, and it also tells me whether the number, the type of the number that it has found, or and whether it kind of overflows its bounds. Um, it also recognizes strings and stores the length of the string as one of the members in the data structure. Um, Moving on, this is kind of the parser. So the parser recognizes the tokens and builds out the tree um, from uh, the from the user program. I've used the Fibonacci sequence over here to demonstrate this. You'll also notice that the parser takes care of associativity of all expressions um, within the within the program. Uh, the next thing that the next stage is the symbol table. So as you can see, the same Fibonacci program has basically been decomposed into the symbol table and the abstract syntax tree, which points into the symbol table. So these are all the identifiers that have been used by the programmer, and these are kind of what these identifiers stand for. So that has been taken care of in the symbol table. The entire type that has been defined by the user has been taken care of. The next stage that I'm going to talk about is the type checking. So this was a little tricky in the sense that we literally had to become like a language lawyer and find all the parts that in the Hubbardston and Steel and kind of go through it. So I'll go through some of the parts that I found were tricky representations of the type checking. So this is like an addition of three nodes. So this is how the output will be in the type checking, and this is how the type tree will be formed for that equivalent expression where the short is casted into an int in both cases, and all of these are added, and the result is kind of converted back into a short by typecasting. So this is one part. The second part is where we had our complex assignment or even the post increment. These are like the side effect operators. So these have also been taken care of in this manner where one of the casts is taken care of as an operand and one of the casts is taken care of as a result. So here we are adding A to C, but we are also casting the result. So that is something, that is another aspect of type checking. And then one of the tricky things that I found was the array assignment. So this is how the entire array is being typecast. So this is being so the output is basically being typecast into um, an, a, an array of pointers, and then from there it's being typecast into a pointer to an int, and then it's being converted to an int and it's being assigned to 0. So just some of the fine aspects of C that I've encountered during this course. And finally, it gets converted into the representation that we saw is now converted into an intermediate representation like this. So this is how it looks like, and it's very close to assembly language. So the key takeaway is that from this course is that it's like a unique blend of theory and practice. I also did a lot of hands-on implementation and design in C. I use a lot of data structures like arrays, linked lists, hash tables, trees, and a lot of recursive algorithms. I learned concepts which I had not done before, like deterministic and non-deterministic finite state machines, LR parsers. Um, I understood a lot of C programming language, which I had not known before. Especially this is especially important because as part of my profession, I work in C on a systems level. Um, I guess that's about it. Thank you. Please let me know if you have any questions. Thanks a lot.